We want to look at this question, which basically talks about how each lecture of this particular course can be independently or boring with probability 0.42 or interesting with probability 0.58, and in the next three weeks there will be three such lectures. And you want to find a couple of probabilities. Now the key word here is independently. Why is that important? So the key word here is independently. Now why is this important? Because let's recall something. Let's recall that if A1, A2, so on and on till AK are independent events, then we can write probability of A1 and A2. The comma signifies and or intersection A1, A3, so on till AK is just equal to the product of the individual probabilities. Generally, when we're finding the probability of probability of intersection of some events, we have to apply the multiplicative rule. But when they're independent, as they're here, then their probability of the intersection, which is represented by this comma here, then is just the probability of their product of the individual probabilities. Okay, right? So it's product of individual probabilities. So that's the key thing here. Whenever you're finding probability involving intersection of some events, in general, you have to apply the multiplicative rule. But when those events are all independent, then in that case, you can write the probability of the intersection as the product of the individual probabilities. So the first part asks us to find none of the 6 lectures will be boring. So probability none boring. So this is essentially the probability the first is not boring and 6 is not boring, so on till 6 is not boring. Since all of them are independent events, we can just multiply the probability of not boring, which is so basically which means interesting, which is 0.58, right? And when we're multiplying 0.58 6 times, you can just write it as 0.58 power 6, because this is essentially 0.58 into 0.58, so on 6 times, right? This is basically this. 6 times, right? So you can just write it as 0.58 power 6. Because they're independent events, that's why we can just multiply the individual probabilities, right? So this just turns out to be 0.0331. So here what we're using is independence. So here what we're using is independence, right? That is the reason we can simply multiply the probabilities for each lecture that they're not boring, right? So part B asks us probability. Exactly 3 are interesting. 3 are interesting and 3 are boring. So now here are the two things that we do need to be careful about. Firstly, the probability exactly 3 interesting. Again, using independence, we know this will be, so we can just multiply the probability of 3 being interesting and 3 being boring because of the because of the independence rule 0.58 power 3, right? So we know okay, the probability either 3 are boring and 3 are interesting, right? And we can multiply the respective probabilities. This is like the probability of 3 boring being multiplied, and this is the probability of 3 interesting being multiplied. Again, this is using the independence rule, right? So this multiplication that we can do like this over here is using independence, right? That is the reason we can do it. But this is not the final answer, right? Because we need to count the number of possible scenarios. What do I mean by this? Let's try to understand this. So counting the number of scenarios. What do we mean by this? Think about, because see, when we're saying exactly 3 are interesting, now the total 6 lectures, it could be the first 3 are interesting, but then it could be the first is interesting, the second is not, then the third is, the fourth is not, and fifth is. There's so many possibilities, right? So we have to consider all possibilities, right? Because it's not like the first 3 are boring and then the first 3 are interesting, or the first 3 are interesting and the next 3 are boring, or they could be any combination of, they could be any permutation of these. So think about arranging these symbols, right? So think about, you want to see how many possible ways we can arrange these symbols, which is it could be interesting. So basically we want to see how many ways can we arrange these symbols, or what are the possible number of permutations of these, right? So number of permutations or arrangements or what we call arrangements. So we want to see the possible arrangements, the number of possible permutations and arrangements in which the lectures can be interesting or boring. So we know, so the number of possible permutations and arrangements are going to be the 6 such symbols with 6 factorial, and we have to divide it by the repetition. So since these 3 are repeated, so it's 3 factorial into, and these 3 are repeated, so it's into 3 factorial, which, so over here, we can just, so we do have to multiply it with this because we have to consider all possible scenarios for 3 being interesting or 3 being boring, which is equivalent to arranging these symbols. Right, so this is 6 factorial divided by 3 factorial into 3 factorial, right? Here, there was no such thing we had to do because this was a probability, none are boring, right? So all of them are interesting, right? So it was these symbols 1, 2, 3, 4, 5, 6, and they can be only arranged in one way, so we did not have to worry about over here. But here, when we say probability exactly 3 are interesting, so sure, we do multiply the probability that 3 are interesting and 3 are boring using independence because they can independently be boring or interesting. But here, we also have to consider all possible scenarios, right? Because any 3 of those could be interesting, any 3 of these could be boring, and we can count the number of scenarios using permutations or arrangements by considering how the number of possible arrangements of these symbols, I, B, 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 right? 3 interesting, 3 boring. So this answer just turns out to be 0.2891. Now let's do part C. C says at least 2 lectures will be interesting. So what we're going to do is we are going to use the complement rule here. Whenever you typically see the at least or at most, that does, so if you, the complement rule does make it easy to solve the problem. Probability at least 2 are interesting is 1 minus the probability 0 are interesting, right? So this is the probability at least 2 are interesting because we know the complement rule says that, probability of A is 1 minus probability not of A. So at least 2 interesting means, at least means greater than equal to, greater than 2 are interesting. So this is 0 is interesting or 1 is interesting. So this is using the complement rule, right? So this is complement rule where we know probability of A is 1 minus probability not A. So we know OR basically means, so basically firstly, so we just apply the complement rule where we said probability at least 2 interesting is 1 minus probability 0 is interesting or 1 interesting, right? We know OR means union, right? So this is 1 minus P0 interesting union 1 interesting, and since these are mutually exclusive, right, you can't, like, you can either have that 0 is interesting or 1 is interesting. It can't be, both can't be true at the same time, and since they're mutually exclusive, we can just add the individual probabilities. So the reason why we can add, so we can write probability 0 interesting or 1 interesting as adding of the individual probabilities, and then because all means union, and the union of mutually exclusive events is just the sum of the individual probabilities. Now let's actually use this. So we already found, so now we want to find the probability 0 are interesting. And so here we just can use independence. The probability 0 are interesting because they're all independently interesting or boring. So we can just multiply the individual probabilities, right? So just multiply the probability of the boring 6 times. So that would be 0.42 power 6. So this is using independence. And then, sorry. Right, and then what you want to do is you want to find the probability 1 is interesting, right? So this could be 1 is interesting. So the probability of that is 0.58. And then 1 is interesting and 6, 5 are boring. So we multiply this with the probability of 5 being boring. And again, like we said, the reason why we can multiply them like this, right, is using independence, right? Using independence is what allows to easily multiply their probabilities, because in the case of independent events, you can write the probability involved in the intersection as a product of the individual probabilities. Right, so but this does not end here. Just like we do need to consider, okay, when 1 is interesting, we want to count the number of different scenarios, right? So let me just write it here. So we do need to counting the number of scenarios, right? Right, so basically here we need to think about arranging, because again over here when we're seeing that, okay, 0 are interesting, so you're just arranging these B, 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 and there's only one way to do this, so here we don't have to worry about. So when we're saying that all are interesting or all are boring, there's only one way that can happen, so we don't have to worry about the number of scenarios. In any other case, we do have to look at the number of scenarios. Because there's more than one possible scenario, because any of those then can be interesting or boring. Think about arranging the symbols. So what are the symbols that we have in this case? So we want to arrange these symbols. So one is interesting and five are boring, right? The reason why we multiply the probabilities because of independence, but we need to consider all the possible permutations or arrangements. So number of permutations or arrangements going to be 6 factorial divided by 5 factorial. 6 factorial, and then you just divide it taking into account the repetition. So the 5 repetitions will be, so we need to divide it by 5 factorial, right? So we do need to multiply this with 6 factorial divided by 5 factorial, right? We do need to multiply it with that. Right, so this is how we can do this. Now, this is like one way we looked at we can do this question using the complement rule, right? So just yeah. So this question, the thing that we learned over here was that, right, one thing that we learned over here was that when you, because you're independent, when you're finding the probability of the intersection, you can just multiply the individual probabilities. You don't have to apply the multiplicative rule where you use conditional probabilities. The second thing we learned here was that sometimes you do have to account for the number of different scenarios for which you consider the permutations, you use permutations and or arrangements for that. Right, when they're all interesting or they're all boring, there's only one possible way that can happen. But when that's not the case, and you do have to count the number of different arrangements, like we did when you wanted to find exactly three were interesting, or at least two will be interesting. Now here we did this question, like we said, using the complement rule. Let's look at an alternative way this could have been done. We hadn't applied the alternatively, we hadn't applied the complement rule. Alternatively, we could have solved probability at least two interesting as we could have done it as when at least two interesting means that two are interesting, three are interesting, or five are uh, at least means greater than equal to, or four interesting or five interesting, as the probability two are interesting, or three are interesting, or four are interesting, or five are interesting, or six are interesting. And we know the norm means union, and because these are mutually exclusive events, the probability of the union is the sum of the individual probabilities. So we just add all these probabilities. So the alternative way to do this question, if we hadn't used a complement rule, would have been to find the probability two are interesting, then add this to the probability three interesting, and add this to the probability four interesting, and so on. And you would have had to find all these probabilities, right? So, but this is more tedious to do so, right? So it's a lot better that you use the complement rule. Typically, when you say at least or at most, you should always, if using the complement rule allows you to solve the problem in a shorter way. We could have done it without the complement rule, but it would have been too tedious. But this is more tedious. So better to use complement rule because there we only need to find two probabilities. The probability 0 are interesting and the probability 1 is interesting. Better to use complement rule, right? And typically when you see at least or more, that's a hint to look, try to see if the complement rule makes it easier to solve the problem.